So we're really at a watershed moment. If we look at the two largest infrastructures that manage the communication network and the power network, both started around 130 years ago, around the same time, with very similar engineering, market, and regulatory structures. And both evolved roughly along the same path. They span quickly through the two wars, post-war, and both even started to deregulate around the same time. So the development for the two networks have been very parallel until about 20 years ago, when the internet started to diverge. So the internet really started taking over the communication network, and the whole telephone network started to evolve into an IP architecture. Completely different architecture in the engineering end, but it has led to dramatic changes in not way beyond communications that has changed the landscape of multiple industries. The hope, perhaps, is that the power network in the coming decades also undergo an architectural transformation with equally large and long-lasting transformations. No one knows, but the hope is that it will. And could transform into perhaps the largest and most complex Internet of Things. So there are many drivers, and we hear two of them. One is because of climate reasons, that the renewables needs to make a bigger role, take a much bigger role than it is now. If you look at the top two economic sectors that consumes the most primary energy, that is coal, gas, petroleums, nuclear, hydrogen, and so on and so forth. The two largest sectors are electricity generation and transportation. If you look at the top two greenhouse emitters in the US, the top two sectors are electricity generation and transportation. They account for more than 50% of the greenhouse emissions. And therefore, if you really want to reduce drastically the greenhouse emissions, we have to first increase the electric vehicle in our transportation portfolio, and also increase the renewables in our electricity generation. And the second is what are the electrification of transportation? And the enablers, again, there are many things that are happening. One of them is that in the last couple of decades, there will be dramatic advances in power electronics. They will give us the ability to implement sophisticated algorithms in the future. Secondly, it is, as we speak, there is a convergence, a much stronger convergence between the power network infrastructure and the IT infrastructure. The deployment of sensing, control, optimization, and communication infrastructure. Here's another example of why renewable is important. If you look at the world's total energy demand, all forms of energy, it's about 17 to 19 terawatt. So whatever that means, if you look at the harvestable solar power over land, then it is multiple times, many times of the world's global energy demand. And therefore, there's always enough energy in nature for all we ever need. It's up to scientists and engineers to capture it, transmit it, and manage it, which is difficult. So some people make a plot of, if we just calculate how much energy that hit the Earth and how much we need to meet all our demand, then we can provide all the energy demands with these little solar farms covered around the world. So those little dots that you see. And therefore, it's really up to scientists and engineers to really build a much more sustainable energy system in the coming decades. And if we project into the future along this trend, then we conclude that the future network will be very different from the traditional network. For example, if you look at the current network, most of the endpoints today are simply passive nodes. In the US, for example, there are about 10 to 20 large centralized power generators. That's what we control. But there are hundreds of millions, perhaps billions of endpoints that are just nodes. So these are machines, these are computers, and electronics, and so on. If we have a large network of passive nodes, it's relatively easy to control, relatively stable. But in the future, we can have a huge network of active endpoints. So these are not just passive nodes, these are PV photovoltaic panels. These can be wind turbines, electric vehicles, smart buildings, smart appliances, and so on. They not only consume They may generate, some may sense, communicate, and act. And therefore, if we have a large network of active endpoints, intelligent network connected, it is both a risk and opportunity. It is a risk because it's hard to control. It's like a fighter jet that we design the fighter jets to be unstable so that we get performance. And then we wrap around the active control. Similarly, with the power network of the future, if we do not control it correctly, then we can have blackouts much more frequently than we do today. So today's power network is actually extremely reliable. The question is that as we evolve into a much more sustainable form in the future, will it maintain the kind of reliability that we see in the last 100 years? The opportunity is that these are active endpoints and these are intelligent endpoints. Therefore, if we control correctly, then we could improve the efficiency, the security, the reliability, and so on. So that's the big challenge that we're interested in. So that's an extremely high-level description of why we're actually smart grid, and it has all sorts of different interesting challenges. So today I'll focus on one little problem. The key message, so I'll start with this slide and I'll end with this slide. So the key message is that we're interested in real-time optimization of a large network of distributed energy resources. And in many power system operations and planning problems, underlying that is a constraint optimization. And then the computational challenge of that problem is implicitly or explicitly solving the set of Hartley equations. But if you look at the network, the power network is actually solving powerful equations for us at scale in real time for free. And therefore, the idea is that perhaps for many operations, we can explicitly exploit the fact that the power network is a powerful solver to help achieve what we want to achieve. If we do that, then we also get an algorithm that will naturally adapt to the evolving network conditions. So the goal of the network is really, the goal of this talk is really to give two examples. One describes the network at a slow timescale, what's called the optimal powerful problem. That describes the network behavior at timescales of minutes or hours and days. So we gave the precise definition of that. Sure. And the second example is a very fast timescale, sub-seconds timescale, where the power network behavior is described by a set of ordinary differential equations. And again, here's this feature where we can exploit the dynamics, the natural dynamics of the power network to achieve what we want to achieve. All right, so the conference is on uncertainty in AI, and the piece on uncertainty is not explicit in the formulations that you can see. But the overdriving theme of having more and more renewables, by renewables I mean wind power and solar power. When we have more and more renewables in our electricity system, then the key challenge is uncertainty. We cannot control how much we can produce, when and where. It's also difficult to predict how much we can produce when and where. So because how do we deal with uncertainty becomes important to the future, which is different from, exactly different from traditional processes. So the details of the talk, the first part here has two subparts. I thought for this audience, since you're interested in optimization, I'll talk a little bit about optimal power flow. So the first part is some interesting development in recent years on convex relaxation of OPF. So OPF is non-convex, right? We see the details of that. And recently, in the last 4 or 5 years, there's been a lot of work on how we deal with this non-convexity of OPF, and especially how we try to solve non-convex problem exactly through semantic relaxation. And that serves as a motivation for the key part of OPF, which is online optimization. So as we see, traditionally, almost all OPF downstreams are offline. But again, in the future, we're interested in real-time optimization of large network ERs. Then I'll describe what any online algorithm and what we understand about that algorithm. And the second part is on low-side frequency regulation. So I define the model and then describe the algorithm and then show you some results. So a lot of people have contributed to the work, and I just want to acknowledge them. The first part, semi-standardization of PF, many people have contributed towards the work, and there are some of them at Caltech. Online OPS started really with part of the thesis of first of the dead style Facebook. And then the dynamics of frequency regulations are people. Okay, so let's start with OPF. So optimal power flow is an extremely important problem. It is solved routinely every day, every hour, problem. To determine, for example, how do we set network parameters, and how do we set tap changes, and settings, and so on. But also how do we price electricity in the market. And it is first formulated in 1962. There's a huge literature. If you look on just about any optimization techniques that people have come up with, to try OPF, it's going to be a yield condition problem. The computation challenge is huge. And therefore, if you look at the practice, what people actually use, the most common method we use is actually linearizing and solving the linear problem. And then once you get a solution, you may not separate out the equations, then they will treat the linear program, and then it is until you get a feasible solution. So again, many algorithms have been tried. Abstractly, OPF is a constraint optimization. We want to minimize the cost, C of x, subject to two set of constraints. Fx equals 0 is a powerful equation. It's described in all physics. And then there's several operational inequalities, operational constraints that are described by several inequalities. Again, the reason this constraint optimization is important is because numerous power system operations or planning problems, like the one that listed here, underlying these applications is this constraint optimization. So in the next few slides, what I will describe is the details of what is this Fx equals 0 and this doesn't spot. So that describes the model. So again, it's a set of alpha equations, is the operational constraints. And then the details are more important, but you can illustrate, point out structure and where the computation challenge is. And again, the key challenge that we will try to overcome is that Fx is not complex, and how do we deal with these non-complexities with some of the implications. And then also motivate the online where how do we solve these kind of problems in real time in the future. Okay, so the rest I'll go to this detail. So I'll describe one model, and there are different models, and here's just one of them, just to give you the sense of what it looks like. So that way is described by a given graph, and in power system we call them the nodes or buses I, J, and K, and on each bus it can be a generator bus, so there can be generation, this can be power plants, or it can be a neutral. It can also be a load bus, so the loads that we have the vehicles or factories and so on. Or if it is an aggregate model, is you can have both generation and load. So the net injection, that is the net thing of the net generation, is described by this Sj and plus J. So Sj is either a complex number or a pair that describes what's called the real power and then reactive power at more J. And so Sj is think of that as a pair of complex number depending on the branches. So between buses I and J is this line that is described by this impedance, Zij, or Yij, which is simply controllable. So Zij is again, you can think of that as a complex number that describes impedance, or sometimes we use it to denote a pair of resistance and reactance. So the other variables are for each node I, there's a voltage Vi, which is a complex number that describes the voltage phase. Small vi is the magnitude square. The important thing is that small vi that we use does not contain phase information, only the magnitude. Ij is the current against the complex number that describes the current phase. The Lij is the magnitude square. So on each line is this Lij and then capital Sij, which describes the real and reactive power Pij. Again, the details are not important. I just want to give you a sense of the point of the structure. So what is the model? The model is simply a set of variables and a set of equations. So these are the variables. The capital Sij, Lij are the lines, the small vi on the nodes, and then the SI. So the equation is this. And again, don't worry about the detail. The first equation says that at every node, the power must be balanced. What comes in and must go out. And the second is simply Ohm's law. But if you look at the magnitude squared, that is a form of Ohm's law. And then third is simply how the power Sij on the branch depends on the voltage and current. Again, look at the magnitude squared. The important point is that so the important point is that the first two set of equations are linear in the variables that we're interested in. Again, the notation is complex, but you should think of that simply is a compact notation for two set of inequalities on the real part and the imaginary part. The third equation, the third set is quadratic, and that is where the non-complex is. Therefore, the OPF is simply we want to minimize the certain cost, and typically the cost functions are some say linear or quadratic. The challenge is the powerful equations that define the physical set. And the challenge in this context, in this particular model, is simply the first set of equations, which is quadratic. So this was proposed back in 1989 to describe what's called radial. Radial simply means that a power network with a true topology. So one natural thing to do is to change the equality into inequality, then we get a simple. And therefore, we get a conversation of OPF. So OPF in general is we want to minimize the function traffic space, subject to two set of constraints. The first set of constraints is simply cost constraint that describes the operation constraint. So for example, the second set of constraint, Ej has a low bar, upper bar, simply means that the voltage at the power level, every point of power level, has a certain nominal value. So for example, at the power output here, the nominal value is 120 volts. So the voltages in the power network needs to be maintained within a tight bound, say 5% of the nominal value. So that's the second voltage constraint. The first voltage constraint is, for example, the capacity of the generator has a low upper bound. So the first set of constraint is operational, describes the optimal constraint, and we are simply cost constraints. The second set of constraint is the powerful equations that we solve, which is not complex. So instead of us trying to solve this non-complex problem, we can solve as a simple relaxation. Then, when we get a solution, then we can check whether the equality is attained in that quadratic equations. If it is, then we get the optimal solution of the original non-complex problem. Otherwise, there are other things one can do. But what is important? So OPF is problem where capital X is not convex, and SOCP, capital X plus is convex. The difference is important that we can solve SOCP and actually get a tight solution, an exact solution. Then you ask, under what condition will this approach work? That is, we can solve relaxation and get an optimal solution. Well, it turns out if the network has a tree topology, there's a set of results that people have derived, sufficient conditions. It will guarantee the SOCP realization will always work. So this is a high-level description of the roughly three sets of sufficient conditions in this approval. The first simply says, if you look at the injection bound, which are the bounds on the SJs, small SJs. If you look at the injection bounds, if the bounds satisfy certain condition, we call the linear separable, then associative realization is guaranteed. The second set of condition is that if the voltage upper bounds are not tight at optimal points, then the associative realization will get is guaranteed. So either one of the conditions will guarantee is sufficient. So let me just look at the time. I think I will skip the details. So the next few slides simply try to give a more precise mathematical description of these two conditions. So I'll skip that. Okay. So with the semi-definite realization, then we can try to get different realizations. With the realizations, we can understand the relationship among the equivalence between different models and different realizations and so on. And then we can try to understand the sufficient conditions that will guarantee that realization will always work. And then we can ask if the realization, which is the first order realization for polynomial optimization, doesn't work, then you can go up the hierarchy and then try to solve it here. There are also other nonlinear global optimization techniques one can apply. With this, we can look at a lot of global processing operations. We can try to solve distributed, let's say, try to solve realization in a distributed manner. So there's a lot of interesting work that can be on top of realization. So let me get to the online OPF. So if you look at all the traditional OPF, whether it's realization, through linearization, and other techniques, they're all offline, which means that we compute until it converges, and then we apply the solution. So for traditional application, that is sufficient. Again, for the kind of future network that we envision, that is not applicable. And therefore, we try to think about the hardware real-time optimization of a large network is used in the future. But the simulation result that I will show you, I will compare the online algorithm, the performance of online algorithm, with the realization. So, realization is using the FOCP realization that I just went through. And we can check if the examples that we try, we always obtain the optimal solution. And therefore, we know we are comparing the online algorithm with the global. Okay, so, all right. Okay, so here's one example of the form where the cost function is simple quadratic, and it means, for example, the fuel cost of the generation. Or it can be if AI is 0, AI is 1, then it means the power loss of the entire network. So these are examples of cost functions that we want to minimize the cost in some way. Over two set variables. So if you look at the network, some devices are controllable, some are not. And in the context that I described earlier, you can think of the loads as controllable, or some generations are controllable, not the renewable generations. But the voltages in the network, which are the states of the network, are not controllable. The power or current on the network branches, most of them are not controllable by us. And therefore, we denote the control variables by X and uncontrollable network states by Y. And in general, it looks like this. We want to minimize the certain cost as a function of controllable or uncontrollable variables. That's assume a separate over X and Y, subject to two separate equations, one is partial equations. And the second are operational constraints, simple cost constraints. The key assumption we make is that the Jacobian derive of partial equations non-singular in appropriate ways. And the implication is that given any controllable variable X, let's assume there's a unique Y X that will satisfy the partial equations. And therefore, we can eliminate Y and formulate OPF only in terms of controllable variables X. So it looks like this. So everything is in terms of X. And now, even though the objective function in the class constraints used to be simple, convex, once we eliminate Y as a function of X, then we get all this non-convexity. Both the C0 function and also the Y as a function. So the next thing one can do is to remove yx less than y bar in non-convex constraints by just putting it in the objective function, adding variable function. And therefore, we arrive at this much simpler form in terms of constraint, where we want to minimize a certain function L in the function x. Mu is the parameter of the area function, subject to over x in this very simple capital X function. And therefore, all the complexity now is in the objective function, in the constraint set, the principal set is suppose that's a problem. And the basic idea is that we will iterate on x through, let's say, simple gradient, first order gradient, for example. And then apply this to t, the intermediate iterates of the algorithm to the network, instead of waiting until it converges. Apply this t to the network, and the network will automatically solve the problem equations and obtain y. Here will be measurements and communications to get y. Let's assume it's centralized. There's also the issues of how we distribute this. Let's ignore that at the moment. So suppose we solve it centralized manner. Then we need the communications to obtain y from the network. And then with y and so t, we will take the least gradient stack is t plus 1 and assign it to these. So that's the kind of value. All right, so a little bit more precisely, then it takes the following form. So we want to minimize L of x over x in the very simple set, and we use the first order gradient set. And then the more physics will help us complete the gradient projection now. So it's a simple non-linear algorithm. What can we say about the algorithm? Right, so you explicitly express the network as powerful solvers, and as we do that, the algorithm will naturally adapt the network involving their own conditions. So what can we say about this? So a few things. We understand the local optimality to be simple gradient. Under certain conditions, we can obtain global optimality. So in general, there's no guarantee. But we can bound the gap between the suboptimality gap between any local optimal and the local optimal. And finally, if the problem is actually evolving, so the network changes over slowly over time. And therefore, OPF changes over time. Can the algorithm track? So in this 10 minutes or so, then we describe precisely what we precise. So the first local optimality is what one would expect under appropriate assumptions, which I can list. Then xt will converge to the set of local optimals. If the number of local optimals is finite, then xt itself will converge. Okay. So under certain conditions, the local result becomes global. The condition is the following. So P0 in the particular formulation that we described appears in the objective function. In the power system, what you describe is where the bulk power network interfaces with the local power network. And P0 represents the real power that we receive from power in the substation. So if this particular function, as a function of controllable variable x, is convex, Vk is the voltage magnitude at every bus in the network, bus K in the network. So voltage magnitude of the network is a function of x. If these functions are concave, so these are the conditions. And then I'll comment on all these conditions recently. But suppose these conditions are satisfied, then if you look at the set A, which is simply that we recall that the voltage has a certain upper bound. Suppose we reduce the upper bound, and we look at a upper bound that is a complex sum of the lower upper bound. So it's slightly less depending on the value A that we choose. For a certain set A that restricts is a subset of the physical set X. So if the convex power of this of the set local optimal in this set A, then all the local results become zero. So we get the optimal. So the main question is, are the assumptions reasonable? and whether this set A is tight. If the assumptions are not reasonable, or the set A is very small, then it's not very useful. So what one can show is that one can choose A so that small a, so that capital A is set, the subset of feasible region that we operate on. We arbitrarily approach the original feasible set. That is the set that is set by both the voltage constraint and also the Y doesn't quite have constraint, the original feasible set. Secondly, if the SOCP of a set of OPF that depends on PC or DK are a set. So I didn't show what the OPFs are, but those OPFs are very simple OPF, one for each P0 and DK. If that OPF is not compressible with SOC relaxation, if the SOC relaxation is a set, then the assumption is true. Now, of course, there's no guarantee SOC relaxation for OPF, or those set of OPF is a set. But we have a lot of empirical evidence that for radial networks with extreme topology, SOC relaxation are very often exact. We also have sufficient reasonability. So what it says is that the assumptions perhaps are not unreasonable. And then later on we see simulation results in fact seem to confirm that. And again, there's no guarantee. So suppose we try to look at the optimality gap between any local optimum and the global optimum. So look at any local optimum in discrete range, and look at any feasible set that is slightly away from the boundary. So this is the and evaluate its cost at the local optimal and at the slightly interior feasible point. We can bound the gap between the two. So the bound rho is some messy expression. But if we look empirically, look at the algebraic test systems and a set of networks from real networks from utility companies, then this rho tends to be very, very small. So what it suggests is that the any local optimum is probably almost as good as any extremely inferior interior feasible point. Of course, the global optimum could be a boundary, and therefore, if the cost function is not very sensitive near the boundary, then the local optimum is probably okay. There is a guarantee, but we see the empirical result. The last thing one can say is about the tracking. That is, suppose what we have been considering is the case where the OPF set, right? So that's the problem that we're looking at. Suppose the problem itself is time variable. And let's describe that by a parameter gamma t. The gamma t could be the uncontrollable loads may change over time. Or maybe the renewable generations may change over time. Or even sometimes the network parameters change over time. So this gamma t describes a certain parameter that it is OPF that varies over time, it's discrete time. So this is the So let's compare the performance of the online algorithm that I described with the global optimum. So what does that mean? So suppose we look at the finite horizon and look at the sum of the costs over time. So the goal standard, the optimal cost, involve solving for the global optimum at each time. So we look at the time t, we get OPF. Suppose we solve it exactly, we get a global optimum. That is x star of t. So x star of t and the corresponding, that is x star. It should be something t. Of t and the corresponding cost. That is the optimal cost. Compare with the cost of the algorithm s of t. So this is the dynamic regression. Then we can show that the dynamic regression depends is upper bounded by two terms. One describes how fast the OPF drifts, and it is described in terms of optimal point xt plus 1 minus xt at the optimum. So if the problem does not drift very fast, then the expectation is that xt plus 1 star and xt star are relatively close. So that's the first term. The second term has to do with the algorithm that we have is simple first order radial algorithm. It's just a local algorithm, and therefore there's always potentially a gap between the local optimal and the global optimal. So there's no way around that. Now, if the drifting OPF does not drift very fast, say less than square root of t in order, then the regret per time, the average regret divided by t, so the first term goes away, and the second term becomes an average suboptimality gap. And therefore, we can bound the per step regret as entitled by some average local bound. And that local bound you can make it small, but at the cost of computation. Okay, finally, let me close the first part by showing some simulations. So there's a set of networks that we use. These are from the utility companies that we work with. So these are real networks, parameters with different sizes. Number of buses describes the number of nodes in the network. The second and the third column describes that we solve. So this is for the static OPF. Not a drifting OPF, but static OPF. If you solve it using SOC relaxation, you can check that indeed you get an optimal solution for every case, and you look at the optimal cost, which is the objective in the second column, and the computation time, embedded, that's the third column. Compare with the integral point method, the online algorithm that I described, that's the fourth and fifth column, the objective. The last two columns is interesting. The error is simply the difference between the objective functions of the SOC realization, the optimal, and the cost of bound. Essentially zero. The last column, the speed up, is the ratio between time, computation times. So for large enough network, then the speed up is zero. Now, what is interesting is that even though the objective functions are very close, we essentially have the same cost. The optimal solutions can be very different. What it suggests is that the objective function is very flat, which is typical. It's a typically U condition for So that's the online. We move to the third part, which is the low-side configuration, so dynamic one. So the motivation is that there's no significant energy storage in the network. And therefore, supply and demand must be balanced at all times and all points of the network. When the frequency deviates, so again, the frequency is throughout the network, is very tightly controlled around the long-term value. It's less than 1%, 0.05 or so percent, depending on the jurisdiction. In the US, it's 60 Hz, in Europe and China, 50 Hz. So when there's a deviation in frequency from this long-term value, what it means is that it's a supply-demand imbalance, and therefore we have to adjust. And traditionally, for 100 years, the thing that we adjust are the centralized generators. So we adjust the supply to be balanced and be demand. What we're interested in is that in the future, there can be hundreds of millions of intelligent nodes. Instead of only adjusting the supply, you can also adjust the demand in concert in order to rebalance. And therefore, how we design the rigorous continuous low-side control to supplement the generator side. There are many advantages that we skip that because of time. How do we design some large-scale low-side frequency control, and how does it interact with the existing generator side? And the literature and so on. Let me just get the model. So the model again is that we have a network, node I and bus I, and These are the fast timescale description of network behavior. It's described as ODEs. A bus can have a generator or both. If there's a generator, then it drives the frequency. And each node I is three set state variables: theta I, omega I, and pi. So these are the phase angle, the frequencies, the power injections. This is some variables. And then there's this demand or uncontrollable loss, or this can represent the loss of generators. The important point is that this is proportional to the frequency pi omega. Omega is the state, and omega, and pi is the product, so the definite product. And then the line connecting I and J has a variable Pij, which is the real power on line. So this is an equation that describes the behavior in it. The only thing to point out is that the last set of equations is not linear. So that's what it is. Okay. So otherwise, you get a linear equations with this non-linear. That's the construction. That's the point. What we control is the PI. So PI is the generator, that is the generator control that we have used traditionally for years. In the future, if I is a low bus, then we can actually control the PI. How do we design controller for the PI? So that's the question. So that to achieve a few things. So let me elaborate on that. Okay, a little more detail on the generator, on the moduling side. If this generator bus and PI is on, if a parameter that we can control directly, it actually has its own dynamics. It has its own inertia and so on, that adds to the difficulty in maintaining stability. If it is some examples, if it is a low, then this is where we can design active controllers. And the question is how do we design this TI controllers? Okay. So, when the network is steady state, then theta dot omega dot equals 0, then it's right in steady state, and everything is fine. When there's a disturbance, then the network gets out of steady state, it behaves according to these equations. And our goal is to design PI for the low buses I, such that you can drive it back to a desirable optimal point. So what does that mean? That's a bit more precise. So that is the network. That's the physical network. This is its own dynamics, and we have control the overall dynamics. But the control goal is to rebalance power to stabilize the frequency, and then to restore the normal frequency. And there's some other goals. We can formalize these goals as an optimization problem. So that's the key. And we can design controllers to rebalance in a way that minimizes the effort for the load to participate. And again, that we can formulate as an optimization problem, and it looks something like this. Again, the details are not important. The important thing is that there's certain optimization problem you can write down that describes precisely the controller. So the design question is that we have on the left, bottom left is the control problem. We have a power network that has its own dynamics. We want to define the controller which could be dynamic, feedback controller, so that it has two problems. First, the closed loop system is a syntactic state that is to actually drive the network back to the equilibrium point. Secondly, we want the equilibrium point to solve this optimization problem on the bottom right that describe our desirable controllers. So how do we design the control box and controllers? So that's the question. And the idea, now, this is a feedback control design. There are many ways one can design this. The interesting twist is that we not only want to stabilize it, we also want to drive it to a particular point. But we don't have a description of the point, except through an optimization problem. So gas inference. How do we design this? There are many possible ways one might go about this, and here's one proposal. And the idea is, what's the key message? That we want to explore the system dynamic, which is described as our network equations, as part of a problem duality. For a certain optimization problem that is slightly modified version of the optimization problem that we are actually using. So the actual optimization problem gives us a guide on how we want to modify the problem. So that when we apply this first order problem to the modified problem, you will take the form of the feedback closed dynamics. So that's the idea. Now, if we can do that, then there are a few advantages. One is that the intrinsic distributed nature of the network, sparsity of the network, for example, translates directly into the distributed algorithm of the network control. Secondly, this approach gives us a very systematic way, a natural way to prove the stability of the total system, and also to prove that in equilibrium, we will actually solve the illusion of optimization problem. So let me just summarize. If we do all these things, what is the result? The result looks like the following. So in traditional frequency control, there's this primary control and secondary control that operate at slightly different timescale. In the primary control, which is the fastest timescale in the traditional power system, on the generator side, it is completely local. That is, each generator will simply measure its local frequency deviation and decide whether it should increase or decrease generation. It turns out you can do that with the load side as well. So every node will sense its local frequency deviation and decide to increase or decrease its consumption. If we do that, then we achieve the goals that we set out. That is, the feedback closed loop system is as a time stable. Secondly, it will stabilize to a point that solves the illusion optimization problem that embodies the controllers. And it's completely local and therefore gets guidance. The traditional controller has also the secondary control where we not only want to rebalance supply and demand. When we rebalance supply and demand, the frequency will stabilize, but it will not stabilize at a normal value. The secondary control will restore the frequency back to normal value. It actually has another goal, which is power systems are separated into different sub-networks. So these are different control areas. And these are under different organizations. And they trade power. So there's an actual power flow between those sub-networks that are determined by economic dispatch, by some economic optimization, and an even slower timescale. And timescales are 50 minutes per hour. When this is balanced, the timeline flow between those areas also deviate from the solution of economic dispatch. That is, they will not be as efficient economically. So another goal of secondary frequency control is to restore the inter-area power flow so that the economic efficiency is retained. Now, if you want to achieve the secondary frequency control goals, which is to restore normal frequency, but also restore the area flows, then indeed you can design those side control to achieve both. And you will take the form where, in addition, unique communication, basically. Currently, if you look at the traditional power systems, the secondary frequency control is solved in a centralized manner within each control area. So each control area has a certain large bulk generators. There's a centralized control center. It will collect data from all the generators and then centrally solve it in a dispatch command. Now, it turns out you don't have to do it in a centralized manner. do it in a distributed manner, but you need communication among the nodes. But communication only between neighbors. So local communication. Then you will take not just the local sensing of frequency deviation as in climate control. You will also have a cyber component where the nodes will communicate with their neighbors. Such as the branch multipliers of the modifier optimization problem that I showed. Then again, if you do that, you have a nice distributed architecture for the system, and you achieve the two goals that we set up design. One is that if you look at a closed system, so this entire system, if you look at this dynamic, is as entirely stable. And therefore, it will converge to an optimal point. Secondly, that optimal point will solve the original optimization problem, and therefore achieve the control goals that we set up. And the first two set of results that I showed you in the last two slides assumes there's no generic design control. Now we can put in all the generic design control, we can put in all the non-linearity in the network. And then show that the original design in the previous slide will work well with the generic design control. That is, again, if you look at the enclosed system with the design control, with the non-linearity, the system is still asymptotically stable. But now we improve this local asymptotically stable. But the equilibrium point is also desirable. That is solving the original optimization problem. So, let me just show you a simulation. So this is simulation. So the algorithm is designed assuming a very simple mathematical model. But then you can apply the algorithm to a much more realistic simulation model without all those assumptions we made in the mathematical model. Then we can simulate and see how it works. And here's one result. If you look at the primary control result. The red curve shows the behavior of the network after disturbance in the traditional control. It is only generator control. The black curve shows if you take half of the control capacity and give it to the load, and you apply the load control algorithm that we designed, and look at network behavior with generator design control with all the non-linearity, all the detailed simulation models. Then it both achieves a better steady state, that is the steady state frequency. This is primary control, and therefore it does not restore the non-frequency. But the steady state frequency is slightly closer with the low side control. The transients are faster. Okay, let me close with earlier slides. The key message is that we're interested again in real-time optimization at scale of large network of distributed energy resources in the future. And for many problems of that kind, the underlying computational challenge is we have to somehow solve either implicitly or explicitly Power equations, both at slow time scale, plus at fast time scale, depending on what the question is studied. And the idea is that the network actually solves powerful equations for us at scale in real time. And therefore, whenever possible, we should think about how to exploit this network as a powerful solvers to achieve the optimization of control goals that we have. And very often when we do that, we naturally come up with an algorithm that is distributed and will also adapt naturally to the network conditions. And I just took 2 examples. I'll close here. Thank you very much.